Hello and welcome to my channel, to this new video on FastRP, Fast Random Projection Graph Embeddings. Now, the authors of the paper claim to have a 4,000 times speedup over the deep walk approach, while still yielding better results on most of the tested datasets. Now, FastRP is a k-step transition matrix plus random projection approach, and what all of that means we are going to explore in this video along a very simple and small example graph. So we are going to do the math so that we all understand what's going on under the hood. Now, the best thing about FastRP is that it's implemented in the Neo4j GDS graph library. So you can use it on your Neo4j graph database out of the box, just using a handful lines of code. Now, first things first, if you like this video, click the like button, or if you want to see more videos like this, please hit the subscribe button. All right, I'm excited. Let's get started. Okay, first of all, if we're talking about graph embeddings in the first place, we want to find a vector representation for each of our nodes so that we can use these vectors to put them into traditional machine learning algorithms, because they only work on data of vector form. However, we don't want to take the node features as we would do with not related data points, but rather we want to capture the graph structure. So we want to capture the context of a node, so which other nodes is each of the nodes connected to, and capture this graph structure in the embedding vectors. So the embedding function we are looking for takes as input our input graph together with the relations, and we want to find a d-dimensional representation for each of the nodes so that nodes with a similar context end up close in the embedding space. So of course we want the d to be much smaller than n, so we want to find a d-dimensional vector for each of our n nodes. So we would end up, as I depicted here, with an n cross d matrix. We have one row for each of the nodes and a d-dimensional vector for each node in our matrix. So that's also a dimensionality reduction, as we can see from here already. As the authors also state in their paper, every graph embedding algorithm consists of two principal steps. The first one is find some node similarity. So we want to find how similar each pair of nodes in the graph is. And based on this node similarity, we would do some dimensionality reduction. Now, the node similarity matrix is an n cross n matrix because we have combinations of two nodes. So we have n nodes in our graph, and we have a combination which is each of the other n-1 nodes. So we would end up with an n cross n matrix. And for example, in the node-to-vec algorithm, which I have done a video about as well, which you can find here, this node similarity would be based on random walks. So from within, so we're starting from each node in the graph and we do some random walk to sample the context of each of the nodes. So in a sense, we're just checking which other nodes can be reached by each node in our graph. And based on this context set, we can, for example, calculate some similarity using Jacquard, which is a set similarity. And the second step in the graph embeddings is always a dimensionality reduction, because our M matrix, our similarity matrix, has such huge dimensions. So for large graphs, this n becomes very large. We want to reduce the second dimension to d, where d is much smaller than n. So for example, we want to find node embeddings of 10 dimensions. We want to end up with a vector of 10 dimensions for each of the nodes. So our resulting embedding matrix is basically matrix n, which has dimension n cross d. In the node-to-vec algorithm, this comes down to learning this d-dimensional vectors using stochastic gradient descent and iteratively optimizing for our objective that nodes with a more similar context end up closer in the embedding space. So here we have an iterative approach, but FastRP does both of these steps differently and therefore yields also this vast speedup. Okay, let's go ahead and talk first about the node similarity matrix and how FastRP is accomplishing it. So as I promised before, we are going to walk through the entire algorithm following along a very simple example with this example graph. So here we can see we have 5 nodes, which is the length of the vertices set, which is 5, and we are going to refer to it as n in our video. And then we have the edge set, and the length of it is 6, so we have 6 edges in our graph. And we are going to refer to the number of edges in our graph as m. And as you can see as well, we have undirected edges here. So we can traverse each of the edges in both directions. So we can go from node 1 to node 2 and the other way around. However, the FastRP algorithm also works on undirected edges and also weighted edges. In our case, we only have weights of 1, so we don't have weights on the edges. And whenever there's a relevance, so if something changes in the algorithm about directed or weighted edges, I'm going to keep it as a side note. Okay, so I said before that FastRP is a k-step transition matrix approach with random projections. And what all of that means we're going to explore now. So from our example graph, we can construct an adjacency matrix, which we are going to call S. And this adjacency matrix can be constructed from our graph by looking which node is connected to which other nodes. So we have a row for each of the nodes here and a column for each of the nodes in our graph. So that's an n cross n matrix because n is the number of nodes. And here we can say, so in row 1, for example, for node 1, we can see that it's connected to node 2 and 3, which is how it is in our graph. And for example, for node 4, we can see it's connected to node 2, 3, and 5. 2, 3, and 5. So that's the adjacency matrix. And in this case, the adjacency matrix is symmetric because we have undirected edges. If we had directed edges, this matrix wouldn't have to be symmetric because node 3 and 4 could be connected by an edge, which is directed, but not the other way around. So one of the entries would be missing. Furthermore, as we have unweighted edges, we only get once in our graph. So the weight for each of the edges is considered as being a 1. And furthermore, like I said before, the adjacency matrix is an n cross n matrix because we could potentially connect from each of the nodes to each of the other nodes. So that's the n cross n matrix. Now we can use this adjacency matrix to find the transition matrix. And the formula for the transition matrix is to multiply from the left the adjacency matrix with the inverse degree matrix. And what it means, we can see on this slide. So we construct this degree matrix by using this formula. So we want to have entries only when I equals j, so only on the diagonal. And what we do is we sum all of the entries in the adjacency matrix for one row and write the sum on the diagonal. So for example, for node 1, if we summed up all the entries in the row, we would end up with a 2 because node 1 has 2 relations to other nodes. So here, what ends up on the diagonal in the degree matrix is basically for node 1, it's out degree, and for node 2, it's out degree, and for node 3, it's out degree. So that's why it's called the degree matrix. So to construct the inverse degree matrix, as we need in our formula, that's basically the inverse of the entry on the diagonal, as our degree matrix is a diagonal matrix. So the inverse degree matrix is 1 over 2 for node 1 and 1 over 2 for node 2, so it's the inverse degree. So 1/2 for node 2 and 1/3 for node 3 and so on. Now, if we calculated the transition matrix now, we would have the inverse degree matrix. So what we have on the diagonal is the inverse of the degree of each of the nodes and the adjacency matrix, which is basically the nodes each of the nodes connects to. And that will result in the adjacency matrix and the transition matrix. So if we, for example, wanted to calculate this entry here, we would use the first row and the second column as we do in a matrix multiplication. And we would see 1.5 times 1, 0 times 0, 0 times 0, 0 times 1, 0 times 0, and we would end up here, so 1.5. So what's happening basically is that we find the distribution for traversing to each of the neighbor nodes of, for example, node 1. So as node 1 has the out degree 2 and connects to 2 different nodes, so the distribution to traverse to each of them is half and half. So as we can also see from this picture for node 1, there's a half probability to go to node 2 and half probability to go to node 3. So this transition matrix is not symmetric anymore. So here in node 3, for example, we had a probability of 1/3 to traverse to each of its neighbors. So with this edge, for example, but starting from node 5, we go to each of the other nodes in half probability. So from 5 to 3, it's 1/2, and from 3 to 5, it's 1/3. And that's the transition matrix. It's basically for each starting node, for example, 1, we have half and half probability to traverse to node 2 and 3. For node 5 or node 4, we would go with 1/3 probability to node 2, to node 3, and to node 5. So that's a transition matrix. The transition matrix, of course, is also of dimensions n cross n, because we got to store each combination of nodes within our matrix. And what it basically contains is what I depicted here as well. What's the probability of given node 1 to end up in node 3, and the probability would be 1/2, as we can query from our matrix now. So we go to node 1 and see what's the probability to end up in node 3. Now the FastRP algorithm is based on the k-step transition matrix. And what it means is basically that we multiply k with itself k times. And what it means is we get all the path you could follow from each of the starting node over k steps. And that's not so intuitive in the beginning. And therefore we are going to look at a to the power of 2, which is basically multiplying a one time with itself. So we want to find out what a squared means. Okay, so here we have a, here we have a, it's the same matrix. So if we wanted to calculate the top left entry of our matrix a squared, we would multiply this row vector with this column vector. So we would have 0 times 0, a 1/2 times 1/2, 1/2 times 1/3, 0 times 0, 0 times 0, and that would end up in a sum. And what it means to make this calculation is we go from node 1 to node 2 with 1/2 probability, as depicted here. And then we multiply it with the probability of going from node 2 to node 1, which is this 1/2 here. So we have 1/2 times 1/2 is 1/4. And it means going from node 1 to node 2 to node 1. So that's this going from node 1 to node 2 multiplied with going from node 2 to node 1. So the probability to follow this path is 1/4. And similarly, going from node 1 to node 3 is 1/2, and we multiply it with the probability for going from node 3 to node 1, which is 1/3, and we end up with 1/6. So our first entry, so the top left entry in our matrix a squared, so a squared 1, 1, is 1/4 plus 1/6. And that's happening for all of the nodes. So the semantics of our a squared matrix is, if we started in any of the nodes, what's the probability to end up in the other node after 2 steps? And now if we apply this matrix k time to itself, we get the probabilities for each node pair, how likely it is to end up in each of the nodes after k steps. This k-step transition matrix is used as the node similarity matrix, which is the n cross n matrix. Now let's have a look at how FastRP does the dimensionality reduction. So we want to multiply our matrix M, which is an n cross n matrix, with some reduction matrix, which is an n cross d matrix, so that we end up with an n cross d matrix as a result. Now in FastRP, we want to use a random projection matrix to do this dimensionality reduction. Now, one of the most important things about our random projections, our dimensionality reduction, is that we want to preserve pairwise distances. Because we have a similarity matrix, we want to basically capture the similarities in our reduced matrix as well. Otherwise, the reduced dimensions wouldn't be of any help for us. So we want to retain our pairwise distances between the vectors while we are reducing the dimensionality. So the authors making use of an axiom saying that the pairwise distances in our reduced or dimensionality reduced matrix, they stay intact if we sample the random projections from a zero mean distribution. So we can construct a random projection matrix, which we're going to call R, and we want to have it of n cross d dimensions by sampling a distribution which is depicted here. So we use the square root of s with the probability of 1 over 2s, and we use entries of 0 with the probability of 1 minus 1 over s, and minus square root of s with probability 1 over 2s. Now we can say this differently. If we replace 1 over s with s hat, we have 1/2 s hat here, 1/2 s hat here, and 1 minus s hat here. So the positive and negative values are sampled with equal probability of 1/2 s hat, which sum up to 1 s hat, and the 0 values are sampled with probability 1 minus s hat. What we can also see is that we have value which would even each other out. So here we have exactly the negative of the positive one. So if we sample them equally likely and they are exactly inverse, we get actually a zero mean distribution because that value here is also 0. So the sum of all of these sampled values will likely to end up being 0. So we get a zero mean for sure. So that's a zero mean distribution. Now by doing this, we can construct our random projection matrix simply by randomly selecting some of these values to construct this matrix. So we have an n cross d matrix. D in our case is 2, so we want to reduce our n dimensions to d dimensions. S we set to 5, which is the number of nodes we have in the graph. And the square root of 5 is 2.2 approximately. So what we do is we construct this matrix by randomly sampling this distribution here. So we end up with a matrix which in this case doesn't actually have a zero mean because it's probabilities and our sample is so small. But in here we have 3 times the value 2.2, 2 times the value minus 2.2, and the rest is zeros. And the more zeros we get, the easier the calculation is going to be, because if we have a 0, we don't have to do the multiplication. So that's why the authors of the paper also keep this value here as large as possible, because as we have more zeros, the calculations become faster when we calculate our random projections. So they recommend to set this S value here to the number of nodes. Okay, the interesting question now is what happens when we apply this random projection matrix to our k-step transition matrix. So our resulting matrix n is the multiplication of our transition matrix A times our random projection matrix R. To calculate the top leftmost entry in the n matrix, we would multiply this row vector of A with this column vector of R. And what you can see what's happening is that the dimensions which are 0 in our random projection vector are basically cancelled out and others are selected by our square root of 5 value. So in this case, the transitions from node 1 to node 3 and 2 and 3 are activated in our random projection vector for dimension 1, and for dimension 2 in our resulting matrix, the dimensions from node 1 to node 1, from node 1 to node 2, and from node 1 to node 4 are activated, while we have a negative factor for the dimensions 2 and 4. So what the random projection matrix basically does is it randomly activates positively or negatively dimensions in our final result. So they basically act as target node masks for the two dimensions. So in our case, we only have two resulting dimensions, which is D. So we have two target dimension masks, and these are the two vectors, and these are applied to all of the source nodes in our transition matrix. And that would lead us to the final result of a k-step transition matrix with very sparse random projections. And the very sparse comes from the zeros in our random projection matrix. So we have many zeros while still preserving pairwise distances in our k-step transition matrix. So that's why the approach is called a k-step random projection with very sparse projections. That's been the heavy lifting, but still we have one more final math chapter for you in this video, because the authors also talk about normalization, so they add it to their approach, and I don't want to keep this from you. Okay, normalization. So the authors in the paper claim that most real-world graphs have a heavy tail distribution. That means that we have quite a few nodes which are heavily connected, and then we have many nodes with rather less connections. And that leads to that the nodes with many connections have a high or a very high impact on our graph embeddings. So what they want to do is to normalize these values so that they are evened out, the very large ones and the very small ones. So what they have in the paper is a quite lengthy argumentation why this makes sense, which I'm going to keep from you. But what I'm going to show you is how they are doing the normalization in the algorithm. So we can construct a normalization matrix L by having entries on the diagonal, which is basically the degree of the node I over 2 times m, where m is the number of edges in our graph. And all of that we take to the power of beta, and beta is the normalization strength. And in our example, I set beta to 1 so that it's easier to understand what's happening. So if we construct this normalization matrix for our sample graph with a beta of 1, we basically get a diagonal matrix. And what it basically does is normalize our node degree by 2 times the number of edges in our graph. So for node 1, we get 2 over 12. For node 2, we get 2 over 12. For node 3, we get 3 over 12. So that's pretty intuitive to basically normalize the degrees by all of the edges in our graph. So the final result would then be we multiply A times our normalization matrix first, and then times R, our random projection matrix. And then we apply A from the left, K minus 1 times to get the K-step transition matrix, which is normalized together with random projections. So the final algorithm that they claim in the paper is basically the same formula, just written down a little bit different. So the resulting matrix for step 1 is called N1, and it's basically our transition matrix times our normalization matrix times our random projection matrix. And then for I equals to K, we just apply A from the left to the matrix from the previous step. And we end up with a new matrix N1, Ni, so for each step. And then the final result is basically the combination of the random projection matrices from all of the steps. And we also add a factor to each of the matrices so that we can basically set the strength for each of the steps individually. And these parameters we can also cross-validate. And the nice thing is the cross-validation of these parameters can be done very quickly, because we don't have to calculate these n matrices all the time, but rather we can store these n matrices and simply change the values of the parameters and evaluate the new model right again without having to do all of that over again, because it stays the same no matter what these alpha parameters are. Okay, so finally I wanted to to show you the results they state in the paper. So they have 4 sample data sets, and here are the number of vertices and edges, and they testing their methods on each of these data sets. And here we can see from that table that on these data sets, the FastRP has a speed up over 4,300 over deep walk, and on that data set it has a speed up of 8,000 times over deep walk. So the FastRP here only runs 33 seconds, while the deep walk takes 3.1 days. Now you could say, okay, they are fast, but are they producing good results? And they're making a statement about that as well. So they're comparing the macro F1 scores of the algorithms on these 3 data sets, and they're basically yielding the best results on 2 of them, and on the third one they are very close to the best result, which in this case is Neo4j. But if we're looking at the speed up, that is a really great alternative, and there's no wonder why the Neo4j GDS library chose this algorithm to implement as well in their library. Yeah, and that's it. So we understood what the FastRP algorithm is, how it works. So k-step transition matrix and very sparse random projections. Sounds very intimidating, but now that we know what's going on under the hood, it becomes quite simple to understand. And I'm very excited about how simple the math is and how well the results are that they are producing. So it's a fantastic work, I think, and I'm happy that this is implemented in the Neo4j GDS as well. So we can use it with just 3 lines of codes to calculate some graph embeddings in our Neo4j graph. Thank you for following. Please leave a like if you like this video and subscribe to my channel. I will produce more content like this. Also leave a comment if you like. And yeah, make sure to tune in for the next video as well. See you then. Bye bye.